Hello, my name is Arjun Dhaliwal, and this is the video submission for the RoboFest 2014 competition. This is my robot, and it is composed of a plywood plate, an Arduino Uno, a battery bank, two gear motors, a color pal sensor, and a Pololu 860 sensor array. The sensors are reflective sensors. The track of the robot would be on a white Bristol board, as seen as the surface of this table. There would be a track composed of black lines of tape, such as this. There would also then be colored nodes, with type differentiated inside the code, by the code run by the robot, or the color of the node. There would also be little extra things inside the nodes to serve as extra pieces of information. The purpose of the robot is to map out all of these nodes and the distance between them. It will then demonstrate the usage of this newly created map, stored in a data structure. It will do this by using the structure to find the path that is the shortest distance from the start node to the end node. The robot will initially enter the track on a single black line made using black tape. It will be following this black line using a form of line following called PID line following, also known as PID tuning. PID stands for proportional integral derivative. The derivative component of this signifies the rate of change, how quickly the value is changing. Integral component stores the overall change through the course of the execution, or the sum of all the instantaneous values counted. The proportional component gives the actual output, or the error multiplied by a constant, where the error is how far the measured value is away from the set point, which is a value that you want. Unfortunately, proportional line following will deviate from the set point quite a lot on its own. That's why we can combine it with the integral component and the derivative component to create extremely accurate tuning. With the Pololu line sensors, there is a library that allowed me to use a function that would return a value from 0 to 5000, giving me the approximate position of the line on the sensor, as you can see here. It will use 2500, or exactly the middle of the array, as a set point, and it will calculate how to change the power difference between both motors to keep the robot on the line while moving. The robot would map the track in a comprehensive way. Each node would have two children. It would be similar to a binary tree. It would map out the two children of the first node it sees, and then immediately move to the first child, follow the line to reach the first child, map out the two children of that child, and then go to the first child of that child, and then so on until it reaches the end. The robot will then move back until it found the node with children who are unmapped. And then it would go to that node, do the same to its first child and the second child, and follow the first child until it reached the end. This code would repeat until the robot was back on the starting node with no children who have unmapped nodes. So the robot would then stop and use the newly constructed data structure to analyze the data it's just gotten. It would use a pointer to move through the map, and it would store all of the pathways from the start to the end in sequences. It would then calculate the length of every single sequence, and then find the shortest sequence. The robot would then follow the sequence to demonstrate the shortest path. This would demonstrate the accuracy of a PID line following system and the application for tuning other systems, the use of data structures to store information, the use of a robot for mapping, and the viability of storing information that is physically read, such as by the color sensor or the reflective sensors. Unfortunately, I encountered problems with the mapping code, so here I can only show you the PID line following code. I will now show you an example of following a straight line, which would be the objective in the node calculations and mapping.